We're live. My guest today is Ismael Hishon-Rezaizadeh. He is the co-founder and CEO of Lagrange. Lagrange is a network for doing cross-chain state proofs and enables new types of interoperability that we haven't seen before. I'm also dying to find out why he thinks interoperability is not a winner-take-all space and IBC is not the answer. So before we get started, make sure to hit the like button, hit the notification bell, and subscribe to get notified when I go live every week. And remember that none of what we discuss here on the Interrupt is an investment advice. If you like this content, please consider staking with us. We're live on Evmos, Quicksilver, and Osmosis. And you should also check out Nebula Summit, which is our developer event happening in Paris this summer. It's on July 24th and 25th. If you haven't got your tickets yet, there's only a few days left to get early bird tickets. And all the information and tickets are available at nebula.builders. My guest, Ismael, is coming up next, right here on the Interrupt. Hey, Ismael, how's it going? You're muted.
It's a great way to kick off the podcast. How are you, Sebastian?
Yeah. Good. It's always weird coming back to my home setup. There's always like a bunch of little technical glitches and issues, and it takes me a couple of interviews to get them kind of ironed out. But yeah, really glad we're getting to have this conversation. Lagrange is a project that I've been following for some time now, and we've been in contact. And I should disclose that I'm an early stage investor in Lagrange, so get that out of the way for listeners and also potentially regulators. And so it's a new concept and paradigm for doing blockchain interoperability, or at least that's kind of the high level pitch. I know that it allows and sort of opens up possibilities for a lot more than just interoperability, but we're going to get into all that today. But first, before we get started, describe a bit of your background, how you got here, and what's the genesis idea for Lagrange, and how do you end up starting this company?
Well, thanks for having me on, Sebastian. So I am an engineering manager by background, and I was a venture capitalist for a bit after that. I started my career leading engineering for digital asset strategy for a large financial services company, Manulife John Hancock, working on some very early embodiments of decentralized insurance products back before the first DeFi summer. After that, I was a venture capitalist. I led data-driven investing and research for a small SF-based fund for about a year and a half. And then about a year ago, I took the plunge into starting my own company, founded Lagrange with my co-founder. And we have been focusing almost exclusively on new forms of cross-chain interoperability that we believe expand the developer space of what can be built in the interchain and in the cross-chain domain in general. When we think of cross-chain, there's existing solutions that we think very highly of. We think very highly of the ZK bridging work, of IBC, et cetera. But there are other problem spaces that aren't well tackled, and that's what we're going for with Lagrange.
Cool. Well, I just realized that all this time I've been pronouncing it wrong. I've been pronouncing it like it's a Z top song. You just pronounced in French. Great. Okay, cool. Yeah, and what's the genesis idea here, and how did you form your team and arrive at building this company?
Yeah. So, when we were looking at the cross-chain space at the foundation of Lagrange, one of the things we realized was that there were a lot of hop-based and intermediary-based protocols that relied on relaying of state and information between chains. And we think of these as traditionally one-to-one communication. We have state on chain A, and you have some intermediary protocol that takes the state from chain A, reaches a consensus over what that is, and writes that to chain B. And that's a very effective paradigm for programmable asset transfers and for generally one-to-one message passing. But it's not a very extensible paradigm for certain types of cross-chain relationships, right? We have potentially thousands of different rollups someday. We have 100 chains in the interchain right now. And there are properties and relationships that form between these different settlement spaces that are dynamic and fluid, wherein you would want to be able to prove aggregate map-reduced properties, for example, across a series of chains on the next chain. So for example, you might want to prove across a vector of n chains, n times m states on the n+1 chain. And that is some of the work that we do. So how do you prove large amounts of aggregated state and analysis of large amounts of aggregated state efficiently between chains?
Yeah, I guess that probably answers part of the question that I addressed up in the intro is that
Mhm.
you were mentioning before we were talking that you think that IBC solutions like IBC and Axelar are not the only solution to interoperability. What's your take here, and where do you see interoperability going, I guess, in the long term? And do you see that
Mhm.
one-to-one interoperability relationships between chains as an issue, like a scaling bottleneck that we'll have to tackle at some point, and like Lagrange
Yeah,
addressing some of that?
I think when we look at cross-chain, there's always going to be the need for one-to-one relationships, but there's also going to be the need for solutions that address more dynamic end-to-one chain communication relationships. And we think of IBC and Axler and cross-chain technologies as the existing ones as a part of the solution. We think on top of that, there are opportunities, in particular with what we're doing with Lagrange, to support more dynamic forms of cross-chain interactions and cross-chain relationships. And when you think about some of these more complicated relationships, pricing, multi-chain asset positioning, cross-chain, cross-margin accounts, you have the opportunity to build things that simultaneously span and really depend on the state that is settled on a whole bunch of different locations. And that's some of the exciting stuff we're doing at Lagrange. We're very much orthogonal, is the way we think of it. Oh, Sebastian, you're on mute.
Yeah, so if we take a step back and look at the different types of bridging that we have. So
Mhm,
currently there are, the predominant paradigm is a sort of, one-to-one, like chain to chain paradigm,
mhm,
where, one chain, as you described earlier, like there's a state that's established here,
mhm,
chain B verifies the state of that chain, and then some event happens on chain B.
mhm,
Typically it's like minting a token and locking token on chain A.
mhm,
That's the way IBC works. That will be expanded for more generalized message passing, but
mhm,
that's sort of how it works. Now there's a sort of paradigm that's built on top of that, which is the Axelar model, where Axelar sort of sits in between all of these different chains
mhm,
that may or may not have the same consensus
mhm,
mechanism, and can't verify each other. And so
mhm,
Axelar, therefore acts as an intermediary in a sense, facilitating
mhm,
recognition of the other chain state. So sending tokens or sending messages from Ethereum to IBC
mhm,
chains, for instance, is a particularly good example of this. I think chains like Polymer, or projects like Polymer, act similarly, than Axelar, although maybe not, maybe less with less trust on the chain itself, since they do rely on ZKP. But it's fundamentally different from the paradigm that Lagrange is operating in, where you're saying here is like some state proofs
mhm,
that any chain can verify, and that can facilitate
mhm.
many to many relationships between chains, that isn't just like a one-way kind of bridge communication as we've typically seen it. um when you talk about that to people,
Mhm.
given that the mindset is current, and sort of narrative is so highly tied to like the latter, um what kinds of reactions do you get from people, and what kinds of new
Mhm.
use cases or new applications does that open up?
That's a fantastic question. One of the things I'd love to add as well we think very highly of the layer zero team, the Polymer team, the Axis team, etc. And we think of what we build as very much orthogonal and very much the ability to create these net new products in the space that now depend on more complicated state. Like there are certain things you should not be using a relay-based protocol for. There's certain things you should be. And when we talk with people, they often try to draw the similarity between what we build at Lagrange and what you build with Axela. And you would say, okay, why would I want to use Lagrange to pass a token versus Axela? And the answer is, well, you don't want to use Lagrange to pass a token. If you want to price something on Arbitrum based on a moving average of liquidity on dexes on Ethereum, Evmos, and Juno, and you want to look at the pricing of a pair of an asset across 3 different settlement spaces and use that as part of a composite analysis or aggregate property of that on, let's say, the N+1 chain, that's what you want to use Lagrange for. When you have these very fluid, large data sets and you want to try to compute out trustlessly composite properties of that data on the next chain.
Okay, and so from that perspective, Lagrange will be specifically tailored to these types of applications, and not like the I guess like the go-to-market for Lagrange will be tailored to these applications, and not so much the cross-chain transfers or the types of use cases that IBC and Axelar and others are going after.
Exactly.
Okay.
And when we think of the future of all of this, when we think of all the places where state and data are going to settle, you're going to need multiple types of interoperability to handle the different types of relationships that exist in that world.
I mean, how do you see that playing out practically speaking? Do you think that applications will leverage different interoperability protocols within the same application? Is that sort of the end game here, where you'll have different interoperability protocols, and it would be akin to saying like some types of traffic will go over TCP/IP and some types of traffic will go over like some other data transfer protocol, right?
Exactly. Okay. I think we're going to see Web3 stacks converge to some of the development paradigms that we've seen dominate in Web2. And I think we're going to see certain types of interaction and transfer protocols function for certain use cases. And then we're going to see the need for other pieces of technology in that stack to be directly suited for the value that they're delivering. So if you need to price something, it's likely not going to be continued relaying of spot prices between a million rollups. It's going to be these non-interactive aggregated proofs. But if you need to bounce assets between different settlement spaces, then bridging is, of course, going to stay the dominant paradigm, or IBC, or any type of more direct transfer protocol.
Okay. All right. Well, let's dive into some of the technical bits here. I mean, I think one of the predominant themes in this conversation is going to be zero knowledge and state proofs. I think a lot of folks are familiar with those terms, but I think it helps just reminding people like what is a state proof and how it relates to a zero knowledge proof, and just sort of setting those some solid bases here so that we can sort of stand upon.
The way I love to describe state proofs is in the lens of what consensus looks like. I think a lot of people think of consensus as this immovable aspect of crypto where you have chains that reach consensus, and that is somehow this black box paradigm. And they don't really think about, well, what goes into consensus and how does one prove it? How would I prove to you, with no assertion over who I am or over the trust in me, some aspect of consensus on some different chain? And that's, in theory, what you're doing with a state proof. So the simplest way I like to think of it is the way a chain is defined is by a genesis block and then a series of rules under which state can be updated and mechanisms to amortize the agency to update that state. So you have a genesis block and a set of rules that define how that state can be mutated and who can mutate it. And those rules, as long as they're correctly enforced, allow you to recursively prove the validity of any block starting with a trusted block. So that could be Genesis, it could be some other trusted block. And then if you have that trust over that single block and you can prove the rules have executed properly to get to the next block, you can prove the state. And that's the principle of ZK bridging. That's the principle in some ways of light client bridging. That's the principle of state proof. It is, how do I indelibly demonstrate to you a property of the validity of a given block header based on a trusted assertion over some previous block header. It could be Genesis, it could be the some inception block, but it is that recursive relationship you're defining.
Now, in the case of Lagrange, does that imply like chain A accessing some data on chain B? Does that imply that chain A needs to have some sort of a client that is reading the chain data? Because okay, sure, you can verify the state, but you're not going to have access to the data itself. Where does that come into play?
That's a very good point. So what zero knowledge proofs enable is for you to offload portions of that computation off chain and execute that in a verifiable fashion. And so without requiring the entire consensus logic or verification of consensus logic to occur on chain in a language that's compatible with the virtual machine of that chain, you can have a verifier contract wherein you can verify that in fact that execution has happened properly off chain or been verified properly off chain, and that there's a proof of the veracity of that verification or of the validity of that verification. And that is where zero knowledge proofs are very powerful when it comes to proving this type of interoperability paradigm. And moreover, the fact that zero knowledge proofs can be incredibly compact at proving a very large amount of execution gives the opportunity and the ability to prove these large consensus relationships succinctly.
So can you explain that? Like, let's bring it back to the applications perspective.
Yeah.
Let's say you're a blockchain application, right? And you're running on your node, right?
Yeah.
Can you describe sort of the steps required to interact with Lagrange and do this execution, right? Perhaps with the use case you described earlier, right? Like check like average pricing on another chain or the price of an asset, and then verifying that data after you've done the computation.
Yeah. So the great thing about what we do with Lagrange is we try to abstract as much of the complexity over verifying chain state and then verifying storage with respect to given block headers from the developer as possible. And I think the average developer should be allowed and able to transact with these complicated multi-chain state properties without having to understand the specifics of how one proves consensus in the zero knowledge context, or how one proves storage in zero knowledge context. So what you would do with Lagrange, very simply, is there's a contract on a given chain that allows you to verify that some group of storage slots with some group of block headers is in fact valid. And some property can be computed across all of that. So for example, you would say, here are the 9,000 blocks that have occurred on a given hour for Arbitrum, with a 0.4 second block time. And here are 2 storage proofs per block showing the price of an asset on 2 sides of a DEX. And now here is an aggregate composite property that can be derived across all of that data. And you can verify that proof, very compact, very cheap from a gas standpoint, that can confer trustlessly that incredibly complicated relationship. The developer just has to call our contract, pass the proof, pass the data, and get back yes or no, is it valid? On the back end, we handle all the complications over consensus proving and rehypothecated collateral proving and storage proving and all of that.
Okay, got it. Now, but in the case of in this case, for instance, would the developer have to say the developer is on osmosis, right? And they're wanting to verify some data over on Arbitrum, right?
Yeah.
Would that application logic also need to be pre-deployed on Arbitrum, or they're doing that off chain? They're executing those computations off chain, checking the Lagrange contract over on Arbitrum, providing the proof, and then receiving the sort of true or false, whether the proof is valid or not. That's right.
Yeah. So that in this situation, they want to verify an Arbitrum the state of osmosis.
Yeah.
Yeah. So they would generate the proof that would show the validity of the state of osmosis over some relevant time points, and then the computation that's executed on that. They take the proof of all of that, and they verify that on Arbitrum, which makes it very easy because we have a JavaScript library on the front end allowing you to derive all of this without having to understand what goes on behind the scenes.
Okay, cool. So let's dive into a little bit more of the the construction of like Lagrange and the the architecture of the network, because I think it's quite different from what what people typically think about when they think about a bridging protocol. Can you describe the network topology and the different sort of deployments that Lagrange will have on different chains and ecosystems?
Yeah. And the way we really think about it is when you are proving the consensus or when you're proving the validity of a block header of a chain or some type of settlement layer or execution layer, what you have to prove is that at some point in time, based on the predefined set of rules, that this is in fact the state. And that's a very dynamic question when you think about app chains, side chains, roll-ups, and general purpose computation chains or general purpose chains, because there's a very specific set of rules across each of those that are defining what is considered valid, what is considered final. And so the way Lagrange thinks about it is very bespoke, where the chains that we support, we have to think very critically about what is in fact considered valid. So one of the first products that we're building are what we call Lagrange state committees. And Lagrange state committees are designed for optimistic substrates and optimistic environments where you don't have a provable validity of finality or provable finality beyond what is defined by game theory over a period of time. Where optimism has one block finality with respect to a validator who can execute the state transitions between B and B prime that are correspond to the transactions of that block and determine whether or not that state mutation from B to B prime occurred properly. And that has one block finality with respect to settlement on Ethereum, same with Arbitrum, same with Base, etc. But with respect to the fraud proof window and the ability to use that state cross-chain, it's historically been constrained by, for example, a 2-week window, because there is not the ability to take that state and verify whether or not there will, in some future point, be the game theoretic relationship that requires that state, that enables that state to be changed with respect to somebody challenging it. And so with what our committees do is we use a large amount of rehypothecated collateral, either through EigenLayer or Restake with Rocket Pool or Lido, to allow independent validators to execute the state transitions between two optimistic blocks and to attest to their validity. So for example, you take your Ethereum validator, and or take your series of Ethereum validators, and you take a Optimism watcher or Arbitrum watcher, and you use your keys from your Ethereum validator to sign the state that your Arbitrum watcher spits out as valid. And across an entire network of Ethereum validators, you're signing that Arbitrum state. And what you can do with that is generate a proof of the validity of that state at a point in time, based on the economic threshold enforced by the sum of the stake held by the Ethereum validators. So you can use the settlement layer of these ORUs to define a finality that is before the game theoretic finality defined by the fraud proof window.
Okay, I see. So what this enables is it effectively enables users to be able to interact, say, with Arbitrum or like an optimistic solution without having to wait for this, the settlement time, this dispute arbitration time that is typically, part of the deal when working with optimistic solutions, right?
Exactly. And in the case of bridging, you can say, I'll trust the bridge to define for me what is final Arbitrum by them executing it. But when you're talking about 1,000 blocks, 2,000 blocks, 10,000 blocks of Arbitrum state, it becomes very difficult to allow the bridge to define that for every single block. And you start wanting to now have time-pointed proofs of the state of Arbitrum that's being defined that you can then execute computation on.
Okay. So there is a Lagrange network. So there is a blockchain that Lagrange is operating that has a validator set. I believe it's a Cosmos SDK chain. Is that correct?
No, we actually don't have a blockchain. So what
Oh,
we have
okay.
is we have a mechanism for the Lagrange state committees where there are a series of nodes that use rehypothecated ETH collateral. So it could, for example, be restaked ETH with Eigenlayer, or it could be rehypothecated ETH collateral through Rocket Pool or through Lido, directly staking. And these nodes, in essence, have a valid BLS key pair for Ethereum consensus, and
Yeah.
they also have a connection to a ORU client or ORU validator that they're running, or some optimistic substrate environment. And they can use the key pair from their ETH consensus client to sign the state of Arbitrum or Optimism, or Base or Polygon.
Okay. I think there's parts of this that are still a little bit unclear. Is this something didn't you guys have, like, I mean, maybe this has changed, because I know you're still sort of making progress on the product, but wasn't there a chain with validators at some point?
We used to have a MPC based structure where
Right.
we would execute. We use a non-interactive key redistribution procedure across a group of nodes, and we'd execute signatures. The problem with a lot of the MPC based structures, or the Cosmos SDK or Tendermint based structures, when people are trying to build these intermediary chains, is you cap out on the validator set size.
Yeah.
Wherein you're capped at 150 or 175 for Atom if you're thinking about Tendermint, or you're capped at like 250 for most of the MPC schemes, where you're now talking about potentially securing billions of dollars of collective cross-chain volume and cross-chain assets, and you have a very small number of nodes who you're trusting to do that. So when you think about these intermediary chains, as you grow the number of connection points surrounding them, you put an increasing pressure on the security of these intermediaries. And you can increase the collateral of the intermediaries in near perpetuity, but then you create huge centralization agency risk, because you still have, if you compromise, 2/3 of the nodes, 101 nodes, you shut off the whole thing, and you could potentially compromise billions of dollars of value. So that's why we've moved to this dynamic structure that is unbounded, where you can execute these attestations, let's say, to base finality, or to the base roll-up state settlement with 100,000 nodes if you really want to. There's no cap or constraint on that.
And so you were talking about Ethereum validators, and so their role. Are you leveraging the existing Ethereum validator set?
Yes, we are.
Yeah. Okay. So you're leveraging the existing Ethereum validator set as a way to kind of bootstrap this verification network.
Exactly.
Okay, got it. Okay, so yeah, talk a little bit about like the BLS aspect here. So
yeah,
how are BLS how BLS signatures different from, say, like MPC? What does that enable? And how do Ethereum validators, say, like onboard this verification network?
Yeah. So I think the way we like to think of it, the value of this is really in the ability to create these unbounded size sets. So if you want to execute an attestation to finality of something, and this is also going to be the case as you talk about roll-ups that settle on the Cosmos, because I think there's some teams who are working on that right now. When you're going to have ORU settle on the Cosmos, you need to define what does finality look like. For example, you have an ORU settling on Evmos. And in that situation, you want to take the collateral of that settlement layer, and you want to take as much of it as possible and put that behind an attestation that, in fact, the state transitions that were purported by the ORU sequencer are in fact valid. And so what we do with, for example, Arbitrum, is we'll take Ethereum validator collateral with Eigenlayer for restaking, or with something like Rocket Pool or Lido in terms of LSDs, and we'll throw that behind and allow people to delegate that to attestations. And so where that's different than MPC is, typically with MPC, you have a series of nodes signing, and if K of n sign, they reach this public key. They reach a known public key. And that allows you to have, the redistribution procedure keeps the key the same as you continue to redistribute and change your underlying signer set. But the signer set is constrained in size. BLS, you don't reach the same signature every time because you can have a very dynamic set of people signing, but these signatures can be aggregated. And you take one of these aggregated signatures across, let's say, 100,000 nodes, and you can verify it very efficiently. This is what Ethereum does as part of consensus. And so one of the innovations that we've done is you take these underlying collateral sets and you look at existing collateral sets and you look at, well, how does Ethereum define its light client? Where you have a randomly selected group of 512 nodes that execute signatures on Ethereum state and implicitly sign the current committee who is designated to sign this block, as well as the next committee to sign the next block. And then, the next block is valid if the committee that signed the next block is in fact the same committee as what was described as next block in the previous block. And so you have these sign-offs that are recursive, where you can verify a given block by verifying it was correctly signed by the next committee nominated by the previous block or described by the previous block. And that can go all the way back to some start point. And that's what we do. We take that same principle of being able to have these large aggregated signatures sign off on current committee, next committee, and then data. And we apply those to this almost extensible new form of light client for optimistic environments.
So you described how this works for optimistic environments. Mm-hmm. How will this facilitate cross-chain communication between, like the EVM space and mm-hmm. say the Cosmos space, like Tendermint or Solana or other ecosystems?
Yeah. So the way we like to think about it is that if you can prove the consensus of a given chain, then you don't need to have any type of bridging or messaging protocol originating from that chain that doesn't just use the proof of its consensus. And at some point, you'll asymptotically converge to being able to prove consensus very quickly for anything that's in fact rapidly provable, even theoretically provable. And so if you're going from something like, let's say, Evmos to Ethereum, and you can prove the consensus of Evmos because the validator set's at 150 and the signature schemes are capable of being proven within a zero knowledge context, then you're not going to be able to need these large rehypothecated committees. You can, for example, in this situation, you can take the proof of the state of Evmos, and you can take, for example, the proof of the state of Juno over a series of blocks, and you can put that into the Lagrange data processing engines, and you can generate proofs of composite properties on top of all of that data. And then you can prove that as well as the proof that these blocks are valid on Ethereum. But let's say you're going the other way, and you want to prove the state of an optimistic environment on a Cosmos chain. What you'll typically need to do is to be able to have something that you're proving to say that this block header is in fact valid. And that's where these state committees provide a great solution to do that. And so if you can prove it outright, just use the proof. If not, then you need these alternative mechanisms.
So what kind of incentive structures do you have here? Well, one, for these signers, right, that are part of this extensible prover network, mm-hmm. and also, the incentive to act honestly. So what's the game theory here with regards to honest participants? Yeah.
So the rehypothecated collateral either restate with eigenlayer or directly with like a rocket pool or a Lido would be slashed in the event that they execute a malicious signature. And so that's the disincentive behind bad signatures, right? There's a severe economic sanction behind doing that. Behind the value behind
how severe is it?
It would be 32 ETH.
Okay.
Per bad
signature. So you'd lose the entire.
You'd lose your entire
stake of your validator. Got it.
Yeah. Okay. So should probably not sign bad roots. And so the benefit of signing the correct root is you'll collect a fee whenever these proofs are used.
Okay. And I mean, for any Ethereum validator, let's say I'm running an at-home validator. What's involved in participating in Lagrange, or is this
Yeah,
more targeted towards sort of more institutional stakers?
it's actually super light, and that's what we like about it. Where all you would need is your Ethereum validator, or any number of keys you have for validating on Ethereum, and one chain that you want, at least one chain that you want to execute these attestations for. And the code that you have to run is a couple thousand lines, maybe. Um, there's complexity over the zero knowledge proofs and the computation we do on our end on these committees to be able to compute these very large recursive snarks. But from the validator standpoint, it's very light. And you run the code, and what it basically does is it takes your Ethereum key and then it executes the necessary verifications on the arbitrary chain, then it signs that data. And then it sends that data to what can be thought of as a proof generation engine.
Okay. Now, so these proof generation engines, are they on every node, or is there like some other participant that is running these?
Yeah, so anybody can run a proof generation engine, but what it does is just aggregate a ton of these signatures, and then generates a succinct proof on them, where it'll verify that with respect to the previous block, or with respect to the previous block that had a current committee, next committee, and then data, that the correct committee assigned the next block. And some people might be familiar with these types of succinct proofs being used on Ethereum for just like client verification, but these are extensible, in fact, with this design to any chain. Where if a chain doesn't have a provable consensus and doesn't have a like client structure that you can easily verify in a snark, you can then rehypothecate collateral from either it or from anything it settles on, and then now have very easy to prove mechanism.
Okay. Now, I know in your previous design, there was a token involved. Is there still a token here in this updated design?
Is this the when airdrop question?
No, I'm just wondering, if there's a,
Yeah,
I don't do airdrop videos, man.
I
That's
know.
not my jam.
I know.
No, no disrespect to anybody who does airdrop videos, but yeah, is there a token here, and if so, what is
Yes.
the role of the token?
Yes, there will be a token. So, we've talked a lot about these rehypothecate committees that execute attestations. I think the best way to think about the overall problem of Lagrange and what we solve is not related to these extensible like client alternative committees. It's really about being able to prove large amounts of aggregate state in a zero knowledge context between chains. And there are fees that are derived from that, and there are fees that are derived from the consumption of these proofs from the like client committees as well. And collectively, those will be part of, will be incentivized with the token, and will feed back into the token, where there'll be cash flows collected by the token, etc.
Okay, and the token will live on which chain? Because as I've understood here, there's no chain. So
yeah, so we'll have to think about where we want to put the token. I think the question of where a token is going to be put is going to become less and less relevant as time goes on, as long as you have a token with sufficient rights wherever Lagrange is deployed. You'll need verification contracts in every chain. You'll likely need rather complicated computational substrates in order to be able to derive these proofs, and then you'll need a place to verify them wherever they need to be consumed. And there'll be the ability to collect cash flows from that, to route those cash flows, and then to govern the cash flows and the underlying contracts. And that's an inherent value that's created that at some point has to be decentralized. Because for this to truly be this extensible piece of infrastructure that applications can rely on, it will need to be governed by users, and it'll need to be governed by people who have a vested interest in its continued success. And we don't believe that comes from a C Corp.
So you talked about deployments. What's the strategy for deploying Lagrange to all these environments. So obviously there's like an EVM component where like Lagrange needs to be implemented as an EVM contract, or say EVM contracts. You probably need like CosmWasm if you want to deploy on Cosmos chains, Solana if you're building over there or whatever. So and then obviously like on Cosmos, some chains don't have an execution environment that is open and permissionless for folks to deploy there. Yeah. So what's your deployment strategy, and how do you plan to deal with those, like, most notably Osmosis, that don't have a permissionless CosmWasm, implementation and are quite, I'd say, opinionated about, bridging protocols that use the chain?
So, I think the benefit of what we do is because we're not doing asset transfers or bridging, all we need is for them to want to consume aggregated multi-chain states. So if Osmosis now says, I want to have awareness of Ethereum state trustlessly for large groups of blocks, or I want to have awareness for Ethereum compatible chain states, or I want to have awareness for app rollup states for a series of blocks, then it would not be able to get that data natively, and it would not be able to bridge it over fast enough. So in that case, you would need to deploy something that allows you to verify these proofs. Whether or not Osmosis sees the need for that, and I think there's always going to be app chains that don't need data, that have a functional purpose that they can execute on incredibly well, and thereby don't need external data, then we won't be deployed there. But I would imagine that you'll need to prove Osmosis state other places, and I hope Osmosis, I hope Sunny will want to prove the state of other people there. You can build some very interesting things that can be downside price protection and price manipulation protection if you're now looking at the prices of assets across a series of other computational environments.
So you talked a little bit about governance a few minutes ago, or you hinted on it. I mean, the idea of governing a set of contracts on different environments and having sort of a native token that is fungible across different environments without a hub-like thing that kind of sits at the middle of all of this. There aren't many examples of this, I don't think. I mean,
I think that's what makes it fun to build. I think that's what makes it fun to build.
Yeah. So how do you how do you see like governance playing out, and what's your vision for how this is going to work?
Yeah, I think we've seen, and hopefully this is not a controversial view, that across the current embodiments of governance protocols, there are some existing issues that have been somewhat public in terms of the ability to vote where wrap tokens are held and have those votes enforced cross-chain in a trustless manner. I also think when we look at some of these more intricate governance protocols, where, for example, you have to actively use an asset for liquidity in order to be given a vote, it makes it very difficult to vote with an asset while simultaneously using it to provide liquidity for something. We look at like what Sushi does with getting votes by being part of the X Sushi to ETH pair. And so when we think of these more complicated governance models, you need tooling that enables them to function in a trustless fashion, trust minimized fashion. And that's one of the use cases Lagrange actually cares a lot about from a product standpoint, as well as one that we hope to adopt as part of our governance model eventually. And from a product standpoint, the simplest form of how I think about it is you have a wrap token on 10 different chains. Every chain has an independent governance contract. You vote wherever you want, and at the end, you take a single proof that sums the votes across the 10 chains, like a Lagrange state proof that aggregates the result of the vote, and you can verify that on any one of the 10. And then you can change the contract there by proving that across the 10 there's quorum.
But what does the orchestration happen? I mean, you would still need some sort of orchestration, wouldn't you?
You don't, because as long any party can aggregate the proof, as long as the information that's being proved is inarguable.
Okay.
And that's where it's interesting, because there's no assertion of trust over who submits the proof, because any one of the chains who gets the proof can verify where it has originated from without having to trust the person submitting it, which means that I can aggregate on my laptop, you can aggregate on yours, plurality of people who can. Anyone can execute, but it must have occurred properly across all 10.
Okay, so anybody could then capture these proofs and send them to the other participants in in this sort of constellation of the Lagrange deployments, you're sort of relying on at least one person doing that in order for it to occur.
Yes, as long as one person takes the proof of the result of the vote on 10 chains and compacts that up, you're good to go.
Okay.
And you don't have to trust that person.
Interesting. Okay, yeah. I mean, I think where else would I? Okay, so yeah, let's talk a little bit about let's talk about the SDK and for application developers and the role of the SDK.
So developer experience is something that's top of mind for us. I think when we look at the ZK space in general right now, a lot of ZK protocols have tenuous developer experience at best, where it is very difficult to interact with any type of computation done in a zero knowledge context without being able to understand what underpins it. And at some point, that's going to go away. And I think one of the most natural places where that separation should be created is between application level developers who are experts in game theory, experts in mechanism design, and the SDKs that they rely on that provide them the ability to access trustless multi-chain data. And that's where we're really drawing the separation. So if you want to build an application that depends on, let's say it's a yield aggregator, and you want your yield aggregator to deploy its assets across 6 different chains, and you want to track the performance of those and then trigger a rebalance whenever a money market on Arbitrum is underperforming a money market on Juno. You want to move the assets from Arbitrum to Juno in that situation. In that case, you'll need to be able to prove the state of all of those in a comparative fashion. And you'll need to do that without having to understand the consensus of all those chains or the finality of all those chains, or understanding how you would prove that in a zero knowledge context, or understanding how you would map an IAVL tree's inclusion proof to a Patricia-Merkle tree's inclusion proof. That all has to occur in the backend. But you need to be able to trust that the computation that occurred is in fact verifiable. And that's what the SDK abstracts away. You can trust the computation happened properly. You can verify the proofs independently. You can verify them on chain. And you don't have to understand the complexities that underpin heterogeneous consensus and heterogeneous data structure inclusion.
Okay, so what I'm beginning to understand here, and maybe this was made obvious, maybe this was obvious before, but it's just kind of clicked, is that this proof verification doesn't happen on the chain application level. It happens on the user application level. So you're not building like, well, so the verification, but like the proving happens on chain, but the verification happens on the user client side. It doesn't happen in a contract. It's not one contract verifying enough.
No, the verification happens in a contract. You aggregate the proofs. You can compute the aggregated proof in your browser. If you would like to verify it in your browser to ensure that it's accurate before you submit it to chain, you can do that. But then the final verification
happens in the browser, right? The computation happens in the browser
to create the proof.
To create the proof, and then the contracts verify each other. Okay, exactly. Now it makes a little bit more sense now.
And the computation can happen anywhere. If you want to put the computation on the server because you want to compute some giant proof, you're more than welcome to.
Right. Okay. So you talked about some use cases earlier, and I know the website has a couple of other use cases that are like this DID KYC use case. Yeah, can you describe some of the other use cases that you guys have are considering and maybe even going to market with?
We're very excited about a lot of the great work being done in DeFi, building anti-fragile applications that are able to be deployed on potentially low liquidity environments and still function as intended. And I think when we think about, let's say, options protocols, derivative protocols, lending protocols that want to now support long tail assets, there is an inherent risk between supporting an asset that is low liquidity from a collateral standpoint and not having your protocol get wrecked. And that's because if you take, let's say, a large amount of collateral that's a liquid on a chain that doesn't have sufficient liquidity to liquidate it, and the protocol and the person defaults and the loan value rises too high and the collateral value drops, then you can't liquidate that collateral and your protocols left with bad debt, holding a bag. And so when you're supporting these more long tail collaterals that you can't ascertain with certainty a priori to liquidation whether or not there'll be sufficient liquidity for you to sell it all. You need to be able to threshold and support liquidity in a capacity that is that takes into account the secondary factors of that chain. How much liquidity is there? What's the volatility of that liquidity? What's the volatility of the price? What's a moving average of those? What is the moving average? Sorry, where is that liquidity located in the chain? If there's 5 dexes, which one has sufficient spot liquidity at the point of liquidation, and which one has sufficient moving average liquidity to be able to confidently support the liquidation volume you have to. So if you're on an L3 selling on an L2 that sells on an app chain in 3 years, how much liquidity is there for wrapped Algorand collateral? These are the kind of questions that you'll need to be able to understand as a DeFi builder and be able to answer trustlessly. That's one of them. So collateral pricing for long tail assets. And fundamentally, there's other ones that we're very interested in as well in DeFi, such as multi-chain yield aggregators that depend on multi-chain asset positionings, cross-chain cross-margin accounts where you can prove the assets you have in one chain or the positions you have in one chain to cross-margin a different chain. We're very excited about things related to credit or longitudinal analysis of the on-chain activity that can be done trustlessly. We're very excited about these more dynamic governance models, and we're also very excited about the ability to prove pricing between chains for multiple dexes, where you can have dexes that almost implicitly share a liquidity pool, where you can use at the point of transaction proofs of the liquidity across a group of other dexes to show that there's in fact some aggregate volume for that liquidity, and that the price that's global is somehow different than the price that's spot on a given instance.
Okay, so then, yeah, maybe let's just stay on this aggregate liquidity use case.
Mm-hmm.
Can you describe how that would work? So would these chains need to somehow have previously set up like something in order to have that aggregate liquidity and capture like that pricing data, or would this be happening sort of on a third party application that is using Lagrange and sort of creating this dynamic between these dexes?
I think at the end of the day, the agency to decide how it's going to be used is going to rest on the developers. But the really simple example I like to give is, let's say you have 3 different dexes on 3 different chains, and you want to ensure that each of these dexes has the equivalent amount of liquidity because you expect an equal swap volume on all 3 of them. And so you want to preemptively ensure they all keep enough liquidity. Right now, you would have to monitor off chain, or you'd have to try to rebalance them somehow. And it would likely not be able to be done in a trustless fashion. What you can do with a state proof is, at the point of transaction, you can include the proof of the liquidity on the other 2 chains on the 3rd chain, or vice versa, any one of the 3. And you can use that to trigger rebalances. You can use that to price by being able to say, a user is going to swap, and as part of their swap, they're going to include a price proof. And the price proof is going to show across the other liquidity environments what the sum of the global price is. And as long as you have these proofs that are fast enough computation on large data, you can do that. So you can have dexes on 3 different chains that price based on a TWAP that's averaged across all 3.
Okay, very cool. So what's the roadmap? What's next for you guys? And we'll expect you to launch, and when airdrop here? What the heck? I'm gonna ask you the question.
Love it. We're one of the first components of our technology that we talked a little bit about earlier, the state committees, will be launching privately in about a month to 6 weeks, probably publicly in about 2 months. And that'll support state proofs on some new environments, the optimistic ones we discussed previously, that you could not currently generate state proofs for. Then the computation at scale of these very large, complicated data relationships will have a lot more coming out of that this summer, both in terms of testnet and use cases and early demos and early products, as well as timeframes to unbounded general purpose computation on large data sets that is highly efficient.
And where can, because I know you're still kind of in stealth mode. I think your documentation is still behind a password. When can people expect to have a little bit more, to read and to sort of take in?
Very soon, very soon. This summer, without question.
Okay.
And anyone who finds this stuff exciting and wants to work with us, feel free to reach out to me directly on Twitter.
Cool. And I'll put your Twitter handle here in the show notes. And I think you guys also have a newsletter sign up on the website. So I guess people could also sign up there.
Yeah.
I should probably also do that as well. Great. Ismael, thanks for coming on. I mean, I feel like I've come away from this conversation with a better understanding of how Lagrange sort of is constructed, and the different moving parts. We'll definitely have to do this again in a couple of months when you guys have launched and have some running code.
I'd love to.
And yeah, thanks again.
Of course. Thank you for having me on the show.
Cheers.
Cheers.